Hey everyone, it's Mr. N here, and this is the 2016 last minute review questions that you wanted me to go over for your last minute study. So let's take a look at these, and the first one says, a camera on the ground 300 meters away from a launch pad records a hot air balloon rising at a rate of 10 meters per second. How fast is the camera's angle of elevation changing when the hot air balloon is 400 meters away? All right, so in this one, 400 meters high, I should say. So in this one, what we've got here is, let me adjust this just a bit more. Okay, what we've got here is a related rates problem, and it's on the ground 300 meters away. So here's the camera, 300 meters away from a launch pad that records a hot air balloon rising. So we've got our balloon here. Not such a good balloon, just deal with me. Okay, and it's rising at a rate of 10 meters per second. So this balloon is going up at 10 meters per second. We can draw a little basket in here. Okay, and we've got this at 400 meters high, and that's our height there. How fast is the camera's angle of elevation? So this is what we're looking for. Changing when the hot air balloon is 400 meters high. So we need our d theta dt is what we're looking for. This is all our givens, and this is what we need to find. So we can set this up by seeing what relates the opposite to the adjacent, and we know that's going to be the tangent of theta. So the tangent of theta relates this opposite, which we're going to call h, and my adjacent, which is x. Well, the adjacent is a fixed value. That's a fixed value at 300. So that's not going to change. So since this is a fixed value, I can just go ahead and substitute that in. So we're going to say the tangent of theta equals h, and I'm going to substitute in this 300. So this just makes it easier when I differentiate each side. You could have left it as x and differentiated it that way. You'll still get the same answer in the end, but it's easier if you substitute anything that's constant and not changing in right now. Since it's not changing, we don't have to worry about the differentiation on it. All right, so we're going to differentiate each side. So on the left side, I'll end up with secant squared theta when I take the derivative of tangent, d theta dt. On the right side, we'll have 1 over 300 dh dt. Now let's substitute the values we have. Do we know what d theta dt is? No. This is what we're solving for. Do we know dh dt? Yes, that's 10. Do we know what theta is? Well, we can find theta because I have the instant when this is 300 and the height is 400. I can solve for this hypotenuse, which is 500, and there's your theta. So since I want secant, the secant of theta is 1 over the cosine, and the cosine is going to be the adjacent over the hypotenuse, so that's going to be 1 over 300 over 500, which will give me 5/3. So that's what this value is right here. So we're going to say 5/3 squared times d theta dt equals 1 over 300, and my dh dt was 10. And at this point, we can go ahead and solve this. And we're going to end up with a value, I'll spare you all the stuff in between, of 3 over 250 meters per second. Or, I'm sorry, radians per second, because this is an angle. So this is a radian per second value. All right, moving on to the next question. A light on the ground is 120 feet away from a building shining at a 6-foot man walking away from the street light and toward the building at a rate of 8 feet per second. How fast is his shadow on the building becoming shorter when he is 40 feet from the building? So here's what we're looking at. We've got someone walking here at 8 feet per second. These are all our givens. And he's 120 feet away from the building. Is shining at a 6-foot man. So a light on the ground is shining, and what we have here is this triangle that's going to be formed, And let's see, how fast is the shadow of the building becoming shorter when he is 40 feet from the building? So in other words, this is my 6-foot man, and here is my building, and this shadow is getting shorter, so we have a dH dt that we're dealing with, and we're moving in this direction at 8 feet per second. So we can set up a ratio here. If we call this our x, we can set up the ratio where we've got 6 to x is going to be our height, this is our height right there, to 120. In case you didn't see what I did, I've got two triangles here. This is x, this is 6, this is 120, and this is my height. So I set up a ratio involving those. So what I can do with this is it can give me one variable in terms of another. So I know the height will be 720 over x. So now I can set this up with what I know. So now I can differentiate this right here. And let's move this a little bit. Differentiate that to end up with my dH dt. So dH dt, I'm going to take the derivative of the left side, is going to end up being, now I can change this to be 720, x to the negative 1 and differentiate it that way. So I'll get negative 720 x to the negative 2 dx dt. Well, I know my dx dt. They gave me that dx dt value as 8. So I can solve for dH dt, the change in the height that's happening there, and that's negative 720 over my x, which I already know as 80. And how did I get the x to be 80? Let me show you that in a second here. So this will be 80 squared, and I need my dH, or dx dt, which I know as being 8. Okay, so now let me show you how I got the x. Well, if this is 120 all the way across, and I want to know when I'm 40 feet from it, that leaves me with 40 plus the 80 gives me the 120. That's where I got the 80 from. Okay, so now continuing on with this problem, I simplify this and I get negative 18/5 feet per second. All right, moving on to number 3. Here's the famous ladder questions. A ladder 15 feet long leans against a house. If the foot of the ladder is moving away from the house at a rate of 2 feet per second, find the rate of change at the top of the ladder on the side of the house when the foot of the ladder is 12 feet from the house. Okay, so we've got our ladder resting up against a wall. The ladder is 15 feet. Here's all my givens. And it's moving away at a rate of 2 feet per second. So it's sliding away in this direction 2 feet per second. So this is our dx dt. And we know that it's when it's 12 feet from the house, so we know that this is 12 feet. And we want to know, find the rate of change at the top of the ladder, so how fast it's going down, which is our dy dt. Now, I could put negatives on this and that, but since they're both going in a negative direction, they'll cancel themselves out, so they'll simplify out. So we're just going to leave it as dy dt, and then the other one dx dt. We'll leave those as positives. Now, this is a Pythagorean theorem problem, so x squared plus y squared equals c squared. So this is what I want to differentiate. So if I take, so we've got x, y, and our hypotenuse c. So let's go ahead and differentiate this implicitly. So we've got 2x dx dt, 2y dy dt equals 2c dc dt. But is the length of the ladder changing at all? No, so that goes to 0. So now I end up with just this part right here. So in this, we're going to end up with 2 And we know the x value is 12, and we know what that's changing at. Again, this is where I could put the negative, but I'm going to end up with a negative on the y. So if you want, you can, but just knowing that they're both in a negative direction, we're okay with that. So we can specify our answer as it's sliding down. So this ends up being 2, and then 2, and I know the y is 9. And how did I get 9? Well, let's do the Pythagorean theorem here. If this is 12 and this is 15, this will end up being 9. So that I want to know at the instant when it's 12, so that's going to give me 9 right there. And I'm solving for this dy dt. So that's what equals 0. Go ahead and solve for dy dt, and look, you will end up with your negative here. Dy dt is going to be negative 8/3 feet per second. So it's sliding down at 8/3 feet per second. All right, so moving on to the next problem. So just be careful with the negatives. That's what I meant in here, is if you want to do that as a negative direction, that's fine. Just know that it's sliding down. So in the end, you have to end up with a negative. All right, real world rate of change. The rate at which people enter the OC fare is on a given day is modeled by the function e defined by that. The rate at which people leave the OC fare, so that's entering, that's leaving, is modeled by that. Both E and T and L of T are measured in people per hour, and T is measured in hours after midnight. It's important to know. The functions are valid between 9 a.m. and 11 p.m. The hours when the OC fare is open. At 9 a.m., there are already 200 employees in the fairgrounds. Okay, so we know that there's an initial value of 200. So that's what gives us this. So we know we have an initial 200 people in. All right. So how many people have entered the fair from 9 a.m. to 6 p.m.? Well, let's change this. Since we're going after midnight, midnight's going to be our 0. 9 a.m. would be 9. And then at 11 or at 6 p.m., that's going to be 18. So we're going to kind of base it off military time here. How much time has elapsed? So the amount of people that have entered, since this is a rate, this is a rate right here, the amount of people that have entered is going to be the integral of that. So a rate is per time. To undo that, I'm going to integrate, and I'm going to get rid of that time factor in there. So we want the integral from 9 to 18 of e of t dt. That's how many people have entered. And you can do this on your calculators, and you'll end up with 6505.18. So we're going to round this to 6505 people. Now, here's my suggestion for you on your calculators. I know I've said this in class, so let me remind you again. These two functions are going to be crazy to constantly enter in and do things with. So on your calculators, if you enter y1 as this e of t equation, put that in, double check it, triple check it, make sure that you have entered this correctly. One of the keys is make sure you've put parentheses on the bottom. y2, this is going to be our L of t. Put this as y2 in your calculator, so you're going to hit graph y1, put it in, graph y2, put it in. And here, again, make sure the bottom is in parentheses, that you're putting it all together, because if you don't, it'll do the order of operations and it's going to do that part first, and then you've got the wrong equation. So double check, triple check, make sure these are correct. And so now when you integrate, all you have to do is, on your calculators, hit FNINT, math FNINT, and you'll get the integral symbol if you have the newer software, and you just go from 9 to 18, and you're going to choose y1, and make sure that this is dx. And again, if it's in t, we're just going to use x, so it doesn't matter. How do we get the y1? Remember, it's that vars feature. So choose vars, function, y1, and then hit that enter. And so that'll help you from having to put these two equations in every single time. All right, so for part B, how many people are in the fairgrounds from 9 a.m. to 6 p.m.? Well, we've already established that 6 p.m. is 18. So how many people are in there? Well, we've got people coming in, we've got people leaving, and we have an initial amount here. So that's what we have to do. We have to add the people that are there, the people coming in, and the people leaving. So in this case, we know we already have 200 people. So we've got 200 people already in there. And the people coming in is the integral from 9 to 18. And the people leaving is also going to be the integral from 9 to 18. So I can keep that the same. And we can say the people entering minus the people leaving. That's how many people are there. This is the net change, is what I should say. And this comes out to be, once you put these in, again, put these two equations in your calculator, do y vars. You could do it all in one step now. You just put y1 minus the y2. That's it. And it would, instead of having to constantly put in these equations, which will be very time consuming and you be more prone to errors. So this comes out to be 3513.22. So we're going to say that this is approximately 3513. So 3,513 people. All right, moving on to C. In part C, it says, if the OC Fair decides to charge $15 for admission until 6 p.m. and $10 for admission after 6 p.m., how much revenue will they generate that day? Well, the revenue is based on just the people entering. We don't care about the people leaving. We don't care about the initial amount, the employees there. They don't have to pay to get in. So we just care about the people entering. And we've got two prices here. 15 for the integral from 9 to 18 of the people entering, and y18 because 6 p.m. is 18. And then we've got the rest. Well, the rest is $10. Now they get a discount for the people from 18 to 23. Now, we chose 23 because in the problem, it stated that they close at 11 p.m. So, we were going to go with that. And this is also of E of T dt. I should put dt's here as well. Okay, working this out, we end up with a total revenue generated of 111,931.59. All right, part D. Is the number of people at the fair increasing or decreasing at 7 p.m.? So at 7 p.m., our T is going to be 19. So working this out, we need E of 19, and we end up with 640 there. L of 19 comes out to be 400. So why did I do that? Well, remember, E of T is the rate of people entering. L of T is the rate of people leaving. So now I want to compare, are there more people entering at this rate or leaving? Because that way I'll know, are we increasing or decreasing? So since this is larger than the L of T, larger than L of T, we have more people entering. So our rate of people entering is greater than our rate of people leaving. And that is our explanation for the problem. All right, now moving on to part E. What is the average rate of people entering the fairgrounds from 4 p.m. until 7 p.m.? So now we've got 4 p.m. and 7 p.m. So let's slide this up a little bit. And then we have to understand what these mean. At 4 p.m., that's going to be 16 in military time, and at 7 p.m. that's going to be 19. So I'm taking a look on the interval from 16 to 19, and I want an average rate, so that's an average value. So this is 1 over, remember, average value, b minus a, so this will be 19 minus 16 on the integral from a to b, so 16 to 19 of entering. So we just are concerned with people entering, so this is our E of t, which we put as y1 in our calculator, so we can just plug this directly into our calculators, and we will get 355 people per hour. So that is the average rate of people entering the fairgrounds. Okay, part F. What is the average rate of change of people in the OC Fairgrounds from 4 to... Explain the meaning and the context of the answer in the context of this problem. Okay, well now, since we have the average rate of change, we want the people entering minus the people leaving. So it's the same type of problem. So we've got 1 over 19 minus 16, and this time, from the same interval, 19 to 6, or 16 to 19, I want the people coming in minus the people going out. So that's what I'm looking for this time. And again, this is just y1 as we did it in our calculators, y2. So you could put this all quickly into your calculators, and you're going to get negative 517.7. So approximately negative 517 people per hour is the average rate of change of the people entering the OC Fairgrounds. Now this is, again, what we just said here. This is the average number of people, and in this case it'll be leaving, since it's bigger and negative, the fairgrounds. Okay, and our last problem here for this one, actually we've got two more. At what time is the number of people on OC Fairgrounds a maximum? So this is, we got to maximize this. So in this one, we need to take the rates and set these equal to 0, because to find a maximum, we have the first derivative and we set that equal to 0. So that's the process we're going to take. We have 200 people initially. So that's not going to matter, because when the park opens, there's 200 people there. We'll just test our values against that initial 200. We'll test our maximum points against that 200 and see which is better. And we can also test it at 11 p.m. So here's what we're going to do. We're going to take our E of t. We will take our E of t minus the L of t and set this equal to 0, because these are our rates. And here we will end up with a certain time when we set this equal to 0. Now you could do this graphically, again, as we have our graphs in our equation. So using our calculator, we end up on this one with t equaling 15.8193. And if you test this against time equals 0, which would be 200 people, and at time equals 11 p.m. at the end, you will see that this value does yield the maximum. So make sure you test the endpoints. You need to test what you would get at 0, time equals 0, which we know is 200 people. You're plugging this value back into the integral, is how we know how many people are there. And then you plug in at 11 p.m. and you will see that this one does end up being the maximum number. And when you look at the graph of this, when it crosses, you have positive slopes. And then at this time right here, then you have negative slopes. So positive slopes to negative slopes does give us that relative maximum. And we know it's absolute because we did test it. Now for part H. Here it says, the integral from 9 to t of e of x minus L of x dx. Explain the meaning of h13 and h prime of 13. Well, h of 13 in this context is going to be the integral from 9 to 13 of e of x minus L of x dx. And this yields the people in the fairground. So this will be the people in, so this will be the total, because we're integrating the total people in the fairgrounds from 9 o'clock a.m. to 1 o'clock p.m. That's what the 13 will yield. So then we look at, what does h prime of 13 mean? Well, h prime of 13, this is a rate. So this is just going to be our E of 13 minus our L of 13. And this is a rate. So this is the change in people per hour in the park at 1 o'clock. So this is the change in people per hour at 1 o'clock p.m. So be careful what h of 13 is and h prime, because h prime is a rate and we're using our rates to get that. All right, moving on to the last one. A water tank at Camp Calculus contains 1,200 gallons of water at time t equals 0. During this time interval, 0 to 18 hours, water is pumped into the tank at the rate of Wt with that equation. During the same interval, water is removed. So we have water coming in, water being removed. How many gallons of water are in the time at t equals 18. So what we need to do here is we've got water coming in, water going out, and we have an initial amount. So we've got 1,200, plus we need to integrate the rates to find out how much total we have. So we have to take the integral from 0 to 18 of this W of t equation minus this R of t dt. And once we integrate that, again, put this in your calculators. You could do y1, y2, y1 put the WT equation, y2 put the R of t equation. Much easier in your calculator because we're going to do more work with this. And you'll get 972.3028 gallons. Okay. Is the amount of water in the tank increasing or decreasing at the time t equals 14? Explain. So we need to find the rates. The rates will tell us if the amount is increasing or decreasing. So what we need to do is say W of 14 minus our R of 14. Plug these values in, and you are going to get 39.4685 minus 33.2232, which is going to be greater than 0. So more in than out. So we are increasing. So the rate is increasing. Okay, part C. At what time t equals for 0 to 18 is the amount of water in the tank a minimum? Show the work that leads to your answer. Well, to find a minimum, we need to, again, take the rates and test the endpoints. Okay, so let's go ahead and graph these rates. So we are going to graph the W of t minus the R of t, and we want to set this equal to 0 because we want to know, again, the critical points. How do we find the critical points maximum? We take the derivative, set it equal to 0. These are the rates are the derivative of this, of our original. So when we do this, we will get this type of curve. It comes down, goes up, comes down, then comes back up, kind of like that. Over here, this is at 7.3335. This point is at t equals 14.0713. So we've got our 2 points. Now notice these are below the axis. These are negative slopes. So if we put this on a number line right here, this is 7.3335, and this is 14.0713. These are negative slopes going to positive slopes. Negative going to positive. So a negative slope to a positive slope gives us a relative minimum. Over here, we've got positives going to negatives, so positive slope to negative gives us the relative maximum. So we are looking at time t equals 14.0713 as a relative maximum. How do we know for sure? Well, we've got to test it against the endpoints. We've got to take the integral and test it against our initial amount, the 1,200, and then our final amount, which would be at the end time. So let's go ahead and test all our values. We're going to test at t equals 0, we get 1,200. We know that's the initial amount. At t equals 7.3335, we are going to get 1,200 plus the integral from 0 to 7.3335 of the in, the W of t, minus the out, the R of t dt. And this comes out to equal 796.1948. let's test t equals, since we're going to do this, let's go ahead and test the maximum because we're going to need it for the next one anyway. At t equals 14.0713. So we'll do the same thing. This is the integral of 1200 plus 0 to 14.707143 of that. And that yields, so let me put these in red so we know what we're looking at. We're looking at this number. We're looking at this number. Let's find that integral. And this comes out to be 1495.0813. Let's put that in red. Now we need one more at t equals 18. At t equals 18, we put in the integral, and we end up with 972, that should be 972.3023. All right, so these are the numbers we're looking at. So we want an absolute minimum here. That's what this problem is asking, and that minimum is going to occur right here. So this will be the minimum is at t equals 7.3335, and our justification is because we found the critical points and we tested all the endpoints. Okay, so for then part D, it's the same thing. This time we're looking for the maximum, and we see that the maximum occurs right here at t equals 14. Let's look at this. This was the number for this, at 14.0713. So the time for which it's a maximum, the maximum occurs at t equals 14.0713 because we tested the endpoints along with the critical points, and this yielded our maximum. So now, for the interval 3 to 14, what is the average rate at which the amount of water in the tank is changing? So for this one, for part E, what is the average rate that it's changing? What we need to do is find an average value. So for this, we're going to say this is 1 over 14 minus 3 times the integral from 3 to 14 of E of t minus the R of t dt, and this comes out to be 34.9091 gallons per hour. That's our average value there. For part F, for t is greater than 18, water is no longer being pumped in the tank, but it continues to be removed according to the R of t. If k is the time at which the tank becomes empty, write but do not solve an expression in an integral that can be used to find the value of k. Well, we're going all the way to k when it's going to be empty. So we've got an initial amount, 1,200, plus what's coming in from 0 to 18, which is our E of t minus the R of t. And then for anything greater than 18, it continues to be pumped out and nothing else comes in. So we need to subtract now from 18 all the way to whatever value k, this R of t equation, until we get 0. That would be how we set it up. So this is everything that's coming in minus the out from 0 to 18, and this one is the out for everything greater than 18, and we want to know when all that will end up being 0. So hopefully this review has helped, and thanks for watching, and I wish you the best on your studying and your test, and as many of you want me to say from now on, thanks for watching. Please leave a like and subscribe. All right, talk to you later. We'll see you later.